So I'm going to start with the practice problem first, just because I think I should have done this one first in class too. Just because I think it's easier to work with an electron first, and then go into using an atom. So with this problem, with any binding energy problem, so I mentioned this in class, but with binding energy, you can relate binding energy to kinetic energy through this equation. Start the slide first just to get this through. So with this equation, kinetic energy equals energy minus binding energy. Okay, now we know that there's a separate formula for kinetic energy, right? So kinetic energy can also equal 1/2 mass times velocity squared, right? So what this means is that if I have an electron that I want to figure out how fast it's going, like the velocity of its electron, I need to first find the kinetic energy, and I can find the kinetic energy through this equation. But in terms of what each energy is talking about, right? So we know that this little theta symbol is the binding energy. And then we know that this energy, it's just like another energy that you're applying, right? So I'm just going to say it's an applied energy. What you need to know is that regardless of what kind of energy I'm calling it, right, the basis of energy in general is still going to use the same formulas. E equals h times frequency, E equals hc over lambda. Yeah, like these formulas, right? So the idea is that, like, just because I'm calling it binding energy, you're still calling it kinetic, still calling it applied energy, there's still energy, so I can still use these formulas. In terms of kinetic energy, however, kinetic energy is specifically the difference between my applied energy and my binding energy. So in this case, what happens is I can say that my E, I can rewrite this equation. So I'm going to rewrite the equation. So this is my, that's my equation. I'm going to rewrite it again. So I'm going to rewrite it as Ke equals hc over lambda minus hc over lambda, right? Or I can write it as Ke equals h times frequency minus h times frequency. Or I can write it as Ke equals h times frequency minus hc over lambda. Or again, I can write it as Ke equals hc over lambda minus h times frequency. The only difference between those two energies, so I'm not just like subtracting itself, it's not going to cancel out. The only difference is that second energy is a binding energy. So I'm not talking about the same wavelength or the same frequency, right? So in this case, each wavelength and frequency in that second position, those are all thresholds, right? So in this case, this is a threshold wavelength. It's not the same as this wavelength. This is a threshold frequency. It's not the same as this frequency. This is a threshold wavelength that if I put into, if I try to solve for the frequency of this wavelength, it's going to be different than this frequency. Same thing with this frequency. If I solve for the wavelength associated with that frequency, it's going to be different from this wavelength. They're different. So when you take the difference, when you take that subtraction, it's going to give you an actual number, and that number is going to give you that kinetic energy. So in terms of finding the velocity of electron, once you've found that difference, then you can take your kinetic energy and you can plug it into this equation and solve for velocity. Okay, so that's just a little intro. So going back to that problem. So what we're going to do is we're going to look at this and we're going to say, well, it's a binding energy problem. So this is going to be my favorite formula for binding energy problems, right? All I need to find out is if I'm trying to find the velocity of the electron, I need to figure out what energy, what is my E and what is my binding energy. Whenever you have the words ejected, threshold, minimum, shortest, stuff like that, like words like that, that means you're talking about the binding energy, right? So in this case, what I'm going to do is I'm going to write my E and my binding energy in different colors so that we know what we're working with. So my regular E is going to be in blue, and my binding energy is going to be in red, so we can follow along. So in this case, I know my binding energy has to deal with, ejection, binding, that kind of thing. So if a laser ejected an electron, that means that this wavelength right here, this is a threshold wavelength. And what does that mean? That means this has to be associated with my binding energy. So in this case, my binding energy, I'm going to use the formula HC over threshold wavelength. So in this case, that means I have 6.626 times 10 to the negative 34 joules times seconds times that 3.00 times 10 to the 8th meters per second over my threshold wavelength. And because we are dealing with these units right here, the joules times seconds and meters over second, remember we need to have the same unit, so that wavelength has to be in meters. So in this case, I need to change 350 nanometers to meters. And if you have done this enough times, you'll know that that's really just 3.50 times 10 to the negative 7 meters. So we're just going to go ahead and solve that. Yeah, I should have done this beforehand. Sorry. Okay, so then our energy ends up being 5.68 times 10 to the negative 19. And this is going to be in joules because we're talking about joules, right? So that's one energy. We got that one part down. Now let's talk about that second energy. Well, if you look at the equation or at the problem, the only other energy that's given is this 200 kilojoules. And it says the energy is added after the electrons ejected, which means that this is the applied energy. This is what we can use. So in this case, we don't actually have to solve for the energy. We could just say that our energy equals 200 kilojoules. Now the problem is we're going to have to subtract these two, so they have to be in the same unit. That means that we have to change kilojoules into joules. What we're going to do, that we have 1,000 joules, 1 kilojoule. So I should know this. Right, 200,000. Right. So in other words, 200,000 joules, or you can just say 2 times 10 to the 4, 5, 5 joules. So then what we're going to do is we found our energy, we found our binding energy, now we can subtract. So Ke equals 2 times 10 to the 5th joules minus 5.68 times 10 to the negative 19 joules go ahead and do that. And because I write these problems, sometimes they don't always work out really well. But in this case, when you subtract these two numbers, they actually end up, because this second number, this binding energy, is actually so small, it doesn't even register when you subtract the two. So in this case, it doesn't always happen this way, but in this case, your answer really is just going to be 2 times 10 to the 5th joules. So what we're going to do then is we're going to take that energy, and now we're going to use our second. So this was the first formula that we had to use. The second formula that we're going to have to use to find the velocity is that KE equals 1/2 mv squared, right? So if I take my kinetic energy that I just found, 2 times 10 to the 5th joules, there's 1/2. The mass is going to be the mass of an electron, right? So that's something that's going to be given to you, 9.11 times 10 to the negative 31 kilograms. My velocity is what I'm trying to find, velocity squared. Now this just becomes an algebra problem, right? So in terms of velocity squared, in terms of solving for velocity, all you're going to do is that you are setting, you're going to divide out v squared equals 2 times 10 to the 5th. We're going to divide that by 9.11 times 10 to the negative 31. And then you're also going to multiply times 2 to get rid of the 1/2, right? So do all that. And in order to get rid of that square, the square root this whole thing. Of course, you're welcome to do this in steps. I'm kind of doing it all at once just so that you can see what's happening. Right, so what we're going to do is find out square root, and this is a super fast number, but we got 6.6. Let me see what my fewest number of sig figs in the problem is, 2 sig figs, right? So 6.6 times 10 to the 17th, and what's my units? Meters per second. So this is my final answer. It seems like a lot of work, and I know, but that's kind of what the idea is. You're really just trying to find out all individual energies to solve for kinetic energy and then solve for velocity. Let's go back to, actually let me leave this up for a little bit. Look at it, absorb it, breathe it, or you can just pause the video as well. Okay, so going back to that problem. So in terms of, we're talking about atoms now. So the thing about atoms is that now we're talking about atoms versus electrons. So you have to think about Avogadro's number. You have to think about if it comes to the point, you might have to think about atomic mass. So in this case, like we did in class, we're trying to find, for part A, we're finding the shortest frequency to remove an electron. Remember what I said, anything about shortest, threshold, minimum, ejected, that's a binding energy, right? So we're trying to find, in this case, we're actually not trying to find the binding energy. We're trying to find the threshold frequency, or the frequency that's associated with the binding energy, right? So usually we would have this equation. I'm still going to keep my energies in different colors just so that we see it. Right? So let's start with our binding energy. Right? In this case, we're not solving for binding energy, but we're just going to do it anyway. So we're relating binding energy to frequency, right? So that means I'm going to use that H times frequency equation. I know my binding energy is given to us right here. Now, I talked about this in class, but remember, when we're talking about energy, energy is always in joules, first of all. It's never in kilojoules, because when we're using it in these equations, these formulas, they have to be given in joules. And second of all, when we're talking about removing an electron or removing like a small particle, we're talking about an atom. We're not talking about a whole bunch of them. We're not talking about a mole, right? We're not talking about 6.022 times 10 to the 23rd atoms of titanium. We just want one of them. So in this case, we need to change these units, kilojoules per mole, into joules per atom, right? Because we're moving an electron from one atom. We're not moving electrons from each atom in titanium. That's a lot. So in this case, what we're going to do is we're going to take that number and we're just going to change that, right? So I'm going to put, you have a lot of side problems going with these things. So you gotta make sure that you can keep track of everything. Right, so I have kilojoules per mole. What I'm going to do now is I'm going to get rid of my kilojoules first. So I'm going to put kilojoule on the bottom because I want to cancel those out. Then I know that I want joules, so I'm going to put 1,000 joules on top so I can cancel that out and get just joules. I'm going to keep this in the same line. I'm going to get rid of moles, so I want moles to be on the top so that they cancel out. Then I want to get rid of moles and I want to place it with atoms. Remember, in 1 mole, there's Avogadro's number, the 6.022 times 10 to the 23rd atoms. Right? So once I go through my dimensional analysis, I can cancel out my kilojoules. Those cancel out. I can cancel out my moles. And now I'm left with joules per atom. Okay, so if I go ahead and do that, dimensional analysis, I'm going to multiply times 1,000. And then I'm going to divide by 6.022 times 10 to the 23rd. Then my final answer will be 5.21 times 10 to the negative 9. And what is it in joules per atom? Right? So now I can go back to my binding energy. Now I can actually use this equation, right? Now I have 5.21 times 10 to the negative 9 joules per atom equals Planck's constant 6.626 times 10 to the negative 34 joules times seconds times frequency. Remember, we're solving for frequency, so we don't know what frequency is. So, right, so in order to solve for frequency, what we're going to do is we're going to divide those two numbers. The frequency is 5.21 times 10 to the negative 9 over 6.626 times 10 to the negative 34. It's going to be okay, so your answer should have come out to be 7.8, and we have 3 days, so 7.87 times 10 to the 24th. And what are we talking about? Frequency. So frequency is going to be seconds inverse, right? So this is part A. A is done. Now, in class, I didn't provide you with the second energy, so now we're just going to work with the second energy. Okay, so now that that's done, we're trying to find the velocity of the electron that's being injected. So in order to do that, what do we have to do? Just like we did in the previous question, we need to figure out what that subtraction is first before we can plug it into that second formula of K equals 1/2 mass times velocity squared, right? We're still using these two formulas. One formula, that second formula, KE equals 1/2 mass times velocity squared. Right, so this is part A. Now we're going to go on to part B. So now that we know, what the binding energy is in the correct units, we're also given that energy, we can solve for KE. Right? So KE equals, I'm going to keep this in a separate color so you can see where I'm getting them from, 45,000 joules. Right? So 45,000 joules, right? And that's going to be subtracted from my binding energy. And I did this again. I'm sorry, I write these from out of, just random. I just pull them out of thin air. So my binding energy is going to be really small. So it's probably not going to show much of a difference, which is fine. But just know in typical practice problems, there will be a difference, right? Joules per atom. Although you have that per atom there, just know that it's not, because the energy that's given in part B is within the same problem, just know that it still has the per atom is implied. You don't have to write it down, just know that it's there. Let me subtract those two. Let me just make sure that there's no difference. Yeah, there's no difference. Let me subtract those two. It's going to be 45,000. Don't get comfortable with this just because, like I said, usually there's a difference. Now I'm going to take that second equation. Sorry, excuse me. Take that second equation and set that equal to my kinetic energy. So 45,000 equals 1/2. We're talking about an electron here. 9.11. 10 to the negative 31. And we're solving for velocity squared. So here we go again. Velocity squared equals 45,000 divided by 9.11 times 10 to the negative 31, right? Times 2 to get rid of that 1/2. And then after all that, square root. And once you do all that, solve for your velocity. So let's go ahead and do that. Okay, so 45,000 divided by 9.11 times 10 to the negative 31 times 2, and we're going to square root. And you should get 3.14, look at that, times 10 to the 17th. And what is this going to be in meters per second? Right. So when we're talking about these binding energy problems, the idea, like I said, is that we're going to be using different energies. So you need to be able to see what wavelengths, what frequencies work with what energies. And yeah, so if you have any questions, please feel free to reach out to me. There's a lot of stuff going on here. I know, but yeah, just feel free to reach out to me.